how far we can get. 7.4 and 7.5, there's a lot of information in it. But it's kind of the same process just over and over. 7.4 is pretty short. It's just 3 theorems. And so it's just 1 page. Let me take roll. I forgot to do that. Who are we missing today? Angelina. And that's it. Maybe she'll show up soon. Oops.
Because half of them don't have covered.
Okay. Okay. So back to what I was saying. 7.4 is basically just going to be 3 theorems. And the whole concept in 7.4 is going to be writing a proportion, cross-multiplying it, and solving for your variable. Okay? The hardest part to 7.4 is going to be recognizing what theorem can I use here. You're not going to have to name the theorem and that kind of thing, but you're going to have to be able to look at your picture and decide, how can I write a proportion from this picture? And so the long way to work the problems is what we've been doing. We've been trying to prove that 2 triangles are similar. And once we've proven that they're similar, then we've had some measurements. And we've been able to look at it and say, okay, if these 2 triangles are similar, now I can say 9/12 equals, okay, we could reduce it, but a proportion is where we're comparing 2 different sets of corresponding sides. So it would equal 5/x. And so the long way is to look at your 2 triangles, try to get them similar. Once you know they're similar, then you compare their corresponding parts and write a proportion and then cross multiply and solve. What we're learning in 7.4 is just basically 3 shortcuts where you don't have to go through the process of trying to prove that they're similar. You don't have to redraw these overlapping triangles and try to compare all of their parts. There's going to be some shortcuts that allow us just to look at the picture and from the picture write a proportion and cross multiply and solve. Okay? So it's using kind of the properties of similar triangles, that their sides are proportional, but it is quicker. So I'm going to go through these 3 different theorems and we're going to look at some examples. The first one is called the triangle proportionality theorem. Again, you're not going to have to write a proof, so it's not about memorizing the name of this theorem. It is just understanding what does it say. Angelina, you want to come grab these? And then when you get a chance, put your homework in the tray for me, okay? So the first theorem says, if you have a line parallel to one side of your triangle, so if you look in the picture, do you guys see that we have a line going through the great big triangle and that line is parallel to one side of our triangle? Okay, it doesn't have to be a line. It could just be a segment. So you may have a picture that looks like this. Still, though, you have a piece of a line that's parallel to one side of your triangle, right? So instead of having to redraw these two triangles, a little one and a big one, and try to prove that they're similar and relabel all their sides, this is going to give us a shortcut. It's going to say that if you have a line or piece of a line parallel to one side of your triangle, then when that line intersects the two sides of the triangle, it's going to divide those two sides proportionally. Here's what that means. When you look at this picture, this line, when it intersects these two sides, splits those two sides into two pieces, right? Those two pieces are AE and EB, or AF and FC. And so what they're going to say is if one line is parallel to the base, then the two pieces that are now divided into are going to be proportional to each other. So AE over EB will always equal AF over FC. Does that make sense? It's just a shortcut. The lines have to be parallel or this does not work. So you have to have the little arrows. If you don't have those, you cannot use this theorem. Are we clear? Okay, so let's look at what that looks like on a problem. So this just says find US. When you look at the picture, do you see a line parallel to one side of the triangle? Yes. Remember, the pieces that are split proportionally are only the two sides that are intersected by the parallel line. I'm going to emphasize this again. Only the pieces that are intersected by the parallel line. So these two pieces and these two pieces. You cannot use the base, the parallel pieces. These are not going to be proportional to these. Are you with me? So I'm going to go back real quick just to make sure, because sometimes this is a mistake I see. EF is not going to be proportional to BC in the same ratio as these are. So you can't use the parallel pieces, only the sides that are intersected by them. Okay? So in this picture, how would we write a proportion using these pieces that have been divided? Say it again. TV over VR is equal to? Very good. SU over UR. If we plug those numbers in, I'm going to erase this so you can see that better. What will that look like with the numbers in place? 4 over 10 equals, and you can call it X, you can call it SU, you can call that whatever you want to. I'll put X since that's what Reese said, over 14. So you guys with me? If you have a parallel piece, it's very simple. It's just part over part equals part over part. And then you don't have that whole proving that they're similar piece. Cross multiply and solve. So if we cross multiply, we get 10x equals what? 56. We divide by 10. What do we get for x? 5.6. And it's exactly 5.6, so it's okay to have a decimal as long as it's not a rounded value. So x is 5.6, which was the value of US. So questions on the first shortcut. Okay, so again, the hardest part is going to be memorizing what are these shortcuts I can use. So remember, if you have two parallel lines in your triangle picture, part over part equals part over part. That's the big idea. Okay, we're going to move on to the second one if there's no questions. All right. The next one, this is just the converse, so it's not really the second theorem, but they may ask you to go back and decide if the sides are split proportionally. So it's going the other direction. Remember, converse switches your hypothesis and your conclusion. So do you see parallel marks on this picture? No. So what they're saying is if AE over EB reduces to the same fraction as AF over FC, if that's true, then you can say that these lines must be parallel. So now we're just going the other direction and trying to prove that they really are parallel. Okay? It's called the converse of the triangle proportionality theorem. So for example, if it says verify that they are parallel, you're going to look at the picture. We're trying to decide if DE is parallel to BC. So we need to write our two fractions and see do they reduce to the same value. So what are our two fractions here? 10 over 15 needs to equal what? Is everybody with Gavin on getting this proportion here? Part over part needs to equal part over part. Okay. Would it have been okay if I would have done 15 over 10 is equal to 12 over 8? Okay, so it doesn't matter. Just don't switch. You can't do 10 over 15 and then come down here and do 12 over 8. So start in the same location, okay? All right, so let's reduce. What's 10 over 15? 2 over 3. What's 8 over 12? Because what goes into 8 and 12? 4. 4 goes into 8 twice. 4 goes into 12 3 times. So if the sides are proportional, if 10 over 15 equals 8 over 12, if 2/3 is equal to 2/3, then you can say that DE is parallel to BC. And all I'm going to require you to do to verify that is to show your proportions and show that they simplify to the same thing. Any questions here? For real, we're all good? Okay. So that's really the same theorem, just going both directions. Here's really the second theorem, and it's called the two transversal proportionality theorem. So basically what this is going to say is if you have 3 or more parallel lines. In this picture, they should have marked, and they didn't, so I'm going to go ahead and mark them here, that these all 3 should be parallel. So mark those parallel. If you have 3 or more parallel lines, and they are intersected by 2 transversals. What are the transversals in this picture? AE. Oops, that's terrible. Let's try again. AE and BF. So do you guys see how those are 2 transversals intersecting our 3 parallel lines? If that's the case, if you have 3 or more parallel lines, but you have 2 transversals, then those transversals are going to divide, or excuse me, those lines are going to divide the transversals proportionally. The transversals are going to be split into 2 pieces. So if you look at the picture, AC over, I don't think it's going to let me do it, maybe, CE is going to be equal to BD over DF. The transversals are split into pieces, and they're proportional. So again, it'll be part over part equals part over part. This is your proportion you can write. Okay, so go to your picture. This looks like it's really hard because it's got all these words, but it's not hard. First thing you need to do is decide what in this picture is going to be the parallel pieces. So it says, suppose that an artist decided to make a larger sketch of the trees. In the figure, they give us AB is 4.5. Notice they've already marked it. BC is 2.6. CD is 4.1. KL is 4.9. They want us to find LM and MN to the nearest 1/10 of an inch. So we get to round. We're looking for LM and then MN. That's our goal. What are the parallel pieces in this picture? The trees. They're going to assume that those trees are planted so that they're perpendicular to the ground. And if they're all perpendicular to the ground, then they're going to be parallel to each other. Now, in reality, those trees are probably not all parallel to each other. But we're going to pretend in our example here that these are our parallel lines. Okay? So then where are the transversals? The trees are the parallel pieces, so what are the transversals? The dotted lines. This is a transversal, this is a transversal. Are you with me there? So what the theorem said is that your transversal is going to be split into pieces. And each of those pieces will be proportional to the corresponding pieces on the other transversal. Does that make sense? So we could say AB over BC is going to be the same as what? This part over this part should be the same as KL over LM. Or BC over CD would be the same as LM over MN. Or AB over CD would be the same as KL over MN. They're all the pieces are going to be proportional. So if you have 5 parallel lines, you're going to have lots of pieces that are proportional. So what we want to do is find LM, let's call it X. What would be a proportion that we could write down that would help us find X? Okay, I heard Reese say 4.5 over 2.6. So he's using this piece over this piece. So he needs to go to the corresponding pieces below. What would that equal, Reese? 4.9 over X. Is everybody following? You're just picking the parts of the transversals to their corresponding parts below. Now we can cross multiply and solve. So we end up with 4.5x equals, somebody help me out. What's what is it? Somebody agree with Tate, check his work. Is it 12.74? Multiply that 4.9 times 2.6. Okay, and then what are we going to do from there? Divide by 4.5. And so x is equal to what? And it said to the nearest tenth of an inch, so what would we say? 2.8. Got 2 people that agree. And what are my units? Inches. So this would be not x necessarily, but LM if we're writing our answer. It's 2.8 inches. Now, do we want to use a rounded answer to solve for other answers? No. So my advice would be to not go back and use this value we found for x because it's rounded. I would probably go back and use the things that I know in my picture to find my next unknown. So what am I looking for now? MN. So let's call it a different variable. How about y? What could I write as a proportion that would have 3 values, not this one, and y? Okay, so I'm going to switch to a different color here. Maybe. I don't know. It's not giving me a color. That's strange. Well, maybe I won't switch to a different color. Won't let me do it here? Yeah, okay. Oh, that's red. I don't want red. Now it says I can't do that. Sorry. I think I know how to use a smart board, and then every day it challenges me. I don't know. Okay. Maybe it will. Nope. It looked like it was going through there for a second. Oh, well. Okay, one more time, Reese. What can I do? 4.5 over 4.1. Is everybody with Reese that we're using this one now and this one? Because we want to find y down here below, but we don't want to use x, so we don't want to use 2.6. So 4.5 over 4.1 equals 4.9 over y. Are we all good with that? Questions? Okay, cross multiply, let's solve. And now we're getting really good at this cross multiplying part. So 4.5y is equal to what? And what do you get? 20.09. And then we're going to divide by 4.5. And what do we end up with for y? Okay, and so it said nearest tenth of an inch, so 4.4 something, it's going to round to 4.5 inches. And that is our value for MN, right? Questions? Okay, so just to make sure we're getting these different theorems straight, the first one said you have a triangle, you have a line parallel, you can do A over B equals C over D. So this is the first one we just talked about a minute ago. And now this one says if you have multiple parallel lines, which I'm going to draw the way that they did here, 3 or more, cut by 2 transversals. Those transversals, not the parallel pieces, but the transversals get split into parts. So this would be A over B equals C over D. A over B equals C over D. Are we okay with that? All right. Last theorem. It's called the triangle angle bisector theorem. And again, I'm not worried about you knowing the names of these theorems, just being able to use them. So when you look at this picture, do you guys see that in this big triangle we have an angle that's been bisected? That's why it's called the triangle angle bisector theorem. It's going to say that if you have a big triangle and you have an angle bisected in your big triangle, that angle bisector, which is AD here, when it goes across through the triangle, it's going to split this side of the triangle into 2 pieces. So we're looking at the great big triangle. Your angle bisector comes through the triangle, splits the third side into 2 pieces. It divides that opposite side into 2 segments, and those 2 segments will be proportional to the lengths of the other 2 sides of the triangle. So in other words, BD over DC here is going to be equal to AB over AC. Now this is one that I have a lot of students make a mistake on. You have to start at the same location in your fractions. So if you start here and go over here, you can't jump up to this side in your proportion. Be very careful. So I'm going to draw it over here one more time. This is saying if you have a triangle and an angle is bisected, when that angle bisector comes over to this side of the triangle, it splits it into 2 pieces. Those 2 pieces, A over B, will be proportional to the other 2 sides. But it has to be in the order where you started. So if you start over here at A, where do you have to start on the next fraction? C. You can't do A over B equals D over C. And that's what I have a lot of students mess up on. So be very careful. It's A over B, come back over here, C over D. These are the 3 theorems for section 7.4. And it is just 3 shortcuts to save us time. So when we look at this example, where is our angle bisector? Okay, this QS is our angle bisector. So it's splitting that opposite side PR into 2 pieces, right? Here and here. And then we have our other 2 sides of our triangle. So what would my proportion look like for my problem here? X minus 2 over X plus 5 equals 32 over 40. So we're doing part over part, then going back to where we started, that side over that side. Okay? And then again, it's just a cross multiply and solve problem. So when we cross multiply here, don't forget to distribute. 40 times X minus 2 equals 32 times X plus 5. We distribute the 40. What do we end up with on the left? 40x minus 80. Be careful to distribute. Equals, Distribute the 32, what do we get? 32x plus 160. From there, what do you want to do to solve? Okay, I heard subtract 32x and I heard add 80. Both of those are going to be done. It doesn't matter which order you do it in. So subtract 32x. That's going to give us 8x minus 80 equals 160. And now we can add the 80. Or you could have done it in the other order. So when I add that 80, that gives me 8x equals what? 240. And then we divide both sides by 8. And what is x equal to? 30. Now be careful. What did the directions say for us to find here? PS and SR. So make sure you read your directions. If you stop right here, you're going to miss points because you didn't actually find what they asked for. So what was PS equal to? X minus 2. So when we plug in that 30 minus 2, what is PS? 28. And then SR is equal to the X plus 5. So when we plug in our 30, what is SR? 35. Remember, you are never putting line segments when you're giving me measurements of distances. Any questions on 7.4? Is this really making sense, the 3 different theorems we have? Okay, and again, we could have went and proven these triangles similar, but then it takes so much longer. So we only want to do that if we have to do that. If we don't have to do that, then we can use these shortcuts. All right, 7.5. So 7.5 is where we get to apply what we're learning for real life situations. Like, why in the world, again, are we doing this whole similarity? Well, in real life, there's a couple scenarios that you might need to use similar triangles. And the first way we've already talked about, and that's model, if you're trying to make a model airplane, a model car, a blueprint of something, a scale drawing. So we're going to actually practice making scale drawings today on this section. The second reason that you might need to use similar figures is if you can't physically measure something. So I know this probably hasn't happened, but let's pretend you're sitting up on the 3rd floor and you're looking out the window and you see the flagpole outside. And you think to yourself, I wonder how tall that flagpole is. But you can't physically measure that flagpole because you don't have anything tall enough to get up to the top of it to measure it. So you can do what are called indirect measurements. On a nice sunny day, you can go stand outside by the flagpole and you know your height. You can have someone measure your shadow. Then you can go over and you can measure the flagpole shadow. And what you've just created, if you're standing parallel to that flagpole so that the sun's coming down and creating the same angles from behind you, then that's going to give you 2 similar triangles. And you can use your height, your shadow, a flagpole shadow, and you can create a proportion that lets you solve for the height of the flagpole. Sure. But let's say that you're out on the farm and you need to know some information and you need it now, okay? So whatever the situation may be, it may not be the flagpole outside. It may have nothing to do with a scenario like that, but if you need to measure something that you physically can't measure, you do what are called indirect measurements. And that's where you compare 2 objects and you see that they're similar and you write a proportion and you solve, okay? And then the other thing is the scale drawings and the real life scenarios where you're needing to scale something to make it smaller or bigger. So that's what we're going to look at today. So I already explained this, Gavin. Right. So you would have to make sure that you are parallel to that flagpole so that the angle of that sun coming down on both your head and that flagpole becomes the same angle. Okay. And as long as you're right next to it, it's going to have that same angle from the sun shining down. You want your person to be aligned to the flagpole. Your shadows aren't going to be the same length, but they're going to be parallel to each other. Does that make sense? If I'm standing right here by Kirsten, she's the flagpole. Okay, so we're standing by each other. The sun's behind us. It's coming down, creating a shadow on the ground. So our shadows are not the same length because we're not the same height, but they're going to be parallel to each other. And then that's going to allow us to have angle similarity because my body is making a right angle with the ground. Her body is making a right angle with the ground. And then we have the same angle coming down from the sun. So we have angle similarity, making our triangles that we're creating similar to each other. Does that really make sense? Okay, and I'll show you a picture of what we're talking about here in a second. Okay, so an indirect measurement is any method that uses a formula, similar figures, and/or proportions to measure an object. So if you're not physically out there with a tape measure or a laser or something to measure your object, then if you're using a formula to find it, that's an indirect measurement. Okay, so we've done indirect measurements all semester long. When you're using Pythagorean theorem, that's a formula, that's indirect. We didn't physically measure the triangle. But we're going to talk about proportions now with our indirect measurements. Okay, this is very important. Whenever your dimensions are given in both feet and inches, which is how you typically express your height, right? You don't go and tell someone, well, I'm 72 inches tall. That's kind of weird, right? You give them your feet and inches. You have to convert them to one measurement or the other. So you cannot give your measurement in both feet and inches. It's either going to have to be in all feet or all inches. And you can decide based on the problem what's easier for you, okay? So we talked about that, how you can have a measurement in a proportion that's different as long as it's this whole object's in meters, this whole object's in centimeters. But you can't have an object measured in 2 units. All right, so here's the scenario, Ruben. We've got Tyler up there. He wants to find out the height of that telephone pole. He measures the pole's shadow and his own shadow. So Tyler is 5 foot 9 inches. His shadow is 7 foot 8 inches. The height of the telephone pole is what he needs to know, but he sees that the shadow of the telephone pole is 38 feet 4 inches. So he's got these measurements that he can actually physically measure, because you can measure something along the ground. It's just harder when you don't have a big boom truck to get up there and measure the height of that telephone pole. So he's going to use his indirect measurements, his proportional sides. His triangles are going to be similar. Again, he took his measurements so that his angles up here are going to be equal to each other. Okay? And so now he has angle similarity. So we can compare these two triangles. But we have a problem first, right? We can't use these measurements in feet and inches. So what do we want to convert them to? Okay, it's fine with me if we convert them all to inches. That's probably the easiest way for you to mathematically think about it so that you don't have fractions. So 5 feet 9 inches, how do we convert that to just inches? Okay, take 5 times 12. What is 5 times 12? 60. And then we want to add to that 9. So how tall is Tyler in inches? 69 inches. Okay, go ahead. Let's convert these other measurements as well. By all means, use a calculator. If you don't have one, you're welcome to jump up and grab one. I haven't, but I probably should. That'd be fun. Should take everybody out and we should do we should go out to the flagpole and actually do it. So can't do it right now because we got to get through this lesson. But maybe if we have some time one day, we can go out and do that. It needs to be a sunny, warm day. So maybe closer to the end of the school year. Okay, here we go. What's 7 foot 8 inches? What did you get? 92 inches. Okay, and what was 38 feet 4 inches? 460 inches. Okay, everybody okay with that conversion? Okay, so now we want to write a proportion. This part should be getting pretty easy after we've done it several times in 7-4. So what will my proportion look like here? 69 inches over H. Okay, so we did the height of the Tyler to the height of the pole should equal the shadow to the shadow. So just being consistent, okay? Cross multiply. We get 92H equals what? With 69 times 460. 31,740. Okay, and again, remember that our units right now are all in what measurement? Inches. So then we're going to take that and we're going to divide it by 92. And what do we get? 345. So that means that the height of the telephone pole here is 345 inches. Would we really want to say that though? No, we would want to take this and convert it back to what? Feet. Now, I'm going to practice this with you with the calculator to make sure that you understand how to get your answer exact in feet and inches. So I'm going to show you up here on the board. Give me a second to open my calculator. Sorry, it takes a second for my calculator to open. Okay, so 345 inches. What are we going to do? Okay, divide it by 12, but you have to be careful. Oops. 345 divided by 12. Oops, I did 11. I don't know what's wrong with my fingers. It's not going, I'm going too fast. Slow down. 3, 4, 5 divided by 12. Okay, so you get 28.75, right? So that's 28 feet, but that's 0.75 of a foot, right? So what do we do with the 0.75 to figure out how many inches we have? We multiply by 12. So what I would do, because sometimes this isn't going to be simple like 0.75. It's going to be 0.321967654. It's going to keep going, right? So I would just subtract the 28 so that I'm left with just the decimal part. This is 0.75 of a foot, and I want to know how many inches that is. So I know that there are 12 inches in a foot. So I'm going to take that and multiply it by 12. I did 11 again. I don't know why my fingers are going too fast. Times 12. Okay, and we get 9. Now, some of you are like, duh, that's 3/4 of a foot, 9 inches. And that's fine, but the numbers aren't always going to work out to be nice and pretty like 3/4, okay? So if they don't, on your calculator, we took our inches, we divided it by 12 to get our feet, and we took our decimal portion only, and we multiplied that by 12 to figure out how many inches did we have left. And if it was a decimal, like 9.7 something, we would just round to the nearest inch. So the height of the pole is 28 feet 9 inches. Make sure your answer makes sense. If you get that the pole's 3 feet tall, obviously that's probably not true. So think about that when you're answering your questions. All right, that's indirect measurements. Any questions on indirect? Okay, I think today's pretty easy as far as like the math behind it. We're just writing all these proportions and cross multiplying. So same thing with a scale drawing. We are going to physically create a scale drawing. A scale drawing just simply represents an object as either smaller than or larger than its actual size. So it's going to make it bigger or make it smaller, like a blueprint of a house. The drawing scale, this is the part we haven't talked about, so I want to make sure we're being really clear here. The drawing scale is different than a similarity ratio. A similarity ratio compares the same units. It's like 5 inches over 13 inches, so my similarity ratio is 5 to 13. Okay? A scale can compare different units of measure. So on your blueprint, it may say 1 inch is equal to 10 feet. Does that make sense? So it's going to compare different units of measure oftentimes. A scale is not the same as a similarity ratio. A similarity ratio has to be the same units simplified. A scale can have different units. A scale is the ratio of any length in the drawing to the corresponding actual length. So if my wall on my blueprint is 1 centimeter, in real life that might be 1,500 meters. So this would be my scale. And notice they're using a colon to show a fraction basically, 1 centimeter to 1,500 meters. Are we okay with what a scale is compared to a similarity ratio? They're kind of the same thing, but a little different because this one is in 2 different units. If I wanted the similarity ratio, I would have to change this from meters to centimeters and then reduce my fraction. And then it would be a similarity ratio. Okay? So, again, we've already said this before, a proportion can compare measurements that have different units, just like we did the day one with the model car. We had a model car that had different units, just like we have done on other problems. So it can have different units in your proportion. So here is another example where we might want to use a scale. On a Wisconsin road map, Kristen measured a distance of 11 1/8 inches from Madison to Wausau. The scale of this map is 1 inch to 13 miles. Now this is probably way back before the day of GPS. So Kristen doesn't have a phone that she can type in her location that's going to tell her, hey, you're this far from your location. She has a paper road map in her car, and she has a handy dandy ruler. And she's able to look at her road map and say, this is 11 1/8 inches on my paper. I need to figure out how many miles I have to drive. Okay, so this is very old school, but bear with me. Sure. We will say Kristen is Amish. All right. Yes, I think they do. Yes. All right. So we are trying to figure this information out. So again, I want to make sure you're with me. This is saying that the scale is for every inch on the map represents 13 miles in real life. So on her map, she physically measures the distance between the 2 cities and gets 11 1/8 inches. So she's trying to figure out how many miles is that she has to drive. So anytime you have a problem like this, you can write a proportion, just like we've been doing all day long. Start with your scale. 1 inch over 13 miles. And then just set that equal to the fraction that's going to help you calculate what you're looking for. So on the map, 1 inch is 13 miles. On the map, what's the distance between the 2 cities? 11 1/8 inches. Keep your inches in the same location. So map to real life, map to real life. So what does she want to know? She wants to know X, the distance in miles. Okay? And then we just cross multiply and solve. So we have 1 inch times X equals 13 miles times 11 1/8 inches. Now, would you like for me to pull my calculator back out and show you how you can type in that mixed number easy? Okay, so we're going to multiply that 13 times 11 1/8. I don't know why I didn't just minimize that. Note for today. Okay, so remember, where did we say we could go on our calculator to get fractions? Math doesn't give us fractions. Math lets us change it to a fraction, but where do we get the little options for different? Alpha, where? Y equals. Okay, we want to type in not an improper fraction, number 1, but a mixed number, which looks like number 2, right? So we're going to choose option 2. And look how it gives us a nice little mixed number. And now we can type it in. So we're going to type in 11 What do we need to do to get to the other little boxes? The right arrow key. And then we'll type in a 1. How do we get down to the bottom? Okay, or just the right arrow key will take you there again. And then we type in the 8. And then how do we get out of our fraction? The right arrow key again. Awesome. Okay. I got you. The alpha button. All right, I'll work on that. Grab a different calculator, okay? Yeah, it's real sticky. I don't know. All right, you guys with me? 11 and 1/8? Then what do we want to do? Multiply by 13. Okay? And look, we get this crazy improper fraction. We don't want that. What do we want? Mixed number. So how do we get it changed back to a mixed number? Alpha, y equals. Which one changes it to? Good. 3. 3 goes from fraction to mixed number or mixed number to fraction, depending on what you want. So 3, and then always you have to enter to tell it to do it. And then here is our awesome answer in fraction form. What did our directions tell us? Nearest mile. So this says it's 144 and 5/8 miles. Would we round up or would we round down? Up, because 5/8 is bigger than a half, right? Or if you aren't sure, you can change that back to a decimal if you need to, if you're kind of confused about your fractions. So I'm just going to minimize that real quick. And so our answer, again, is going to be in what units? Miles. The reason it's going to be in miles is because if we divide both sides by 1 inch to solve for x, dividing by 1 doesn't change our number, but it cancels out our inches. And so we're left with miles. Again, if the units are confusing you, you don't really have to put them in your work because we already know that our answer is going to be in miles since we're calculating it to the nearest mile. But it's good for chemistry and physics and physical science that you're practicing those skills. So it was 145 miles. Questions? So one more time, if they give you a scale, write it as a fraction, and then write a proportion with the other information that they give you and a variable for what you're looking for. Every time you can take that scale and make a proportion, and that will let you find whatever you need for your problem. Okay, so now we're going to do it to create an actual scale drawing. So everybody's going to need a ruler. Jump up and grab one real quick. Just make sure, does it work still? Okay. Okay, so ruler's down. Look up here. It says Lady Liberty holds a tablet in her left hand. The tablet is 7.19 meters long, 4.14 meters wide. If you made a scale drawing using the scale of 1 centimeter to 0.5 or 0.75 meters, what would the dimensions be to the nearest tenth? And then create that scale drawing. So first of all, you got to get in your mind what you have here. You have a tablet that's going to be in the shape of what kind of shape? A rectangle. We got a different length than width, and so we're talking about that's something that looks like this, right? It's 7.19 meters long, so I guess it really looks more like this. And it is 4.14 meters wide. And we want to create a scaled down version. We want to go from meters to centimeters so that we can actually draw it on our paper. Okay? So we're going to scale this down. Our scale factor is 1 centimeter is equal to 0.75 meters. You're going to need to do this how many times to find the new length and the new width? Twice. Don't get confused and think you use all of this at once. Write your proportion, that 1 centimeter, is the same as 0.75 meters. And then convert each measurement. So start with length first, and then we'll go back and do width. So this is to calculate the length. So to calculate the length, we know that 1 centimeter is the same as 0.75 meters. We know it is 7.19 meters long. Where is that going to go in our other fraction? The bottom. Keep your meters in the same spot. What do we want to put on the top? X. We're trying to find the length. So now we're going to cross multiply and we're going to solve. So we have 1 times 7.19 is just 7.19 equals 0.75 times X. What do we do to solve for X? Divide by 0.75. So on your calculator, take 7.19, divide by 0.75, and what did it tell us to round to? Nearest tenth. So what do you get for the length? 9.6, and what are our units of measure here? Centimeters. Okay, we're going from meters to centimeters. We're going to do it one more time to find the width. Same process. Start with your scale. Your scale was 1 centimeter to 0.75 meters. And then set it equal to your dimension and put a variable for the one you're looking for. So what's the actual width of the tablet? And so where do we want that to go in our fraction? Bottom, because we want it in the same location. Centimeters to meters has to stay centimeters to meters. So it is our scale drawing to the actual tablet, our scale drawing to the actual tablet. So 4.14 meters. What's going to go on the top? A variable. I'm going to use a different one just to show it something different. So I'm going to use y. Cross multiply. And now we have 1 times 4.14 is just 4.14 equals y times 0.75 is 0.75y. What do we do there? Divide by 0.75. And what do we end up with for the width? Okay, so the width is equal to 5.5 centimeters. Is that rounded to the nearest tenth? Okay, so now you're going to take your ruler and you're going to actually create this scale drawing on your paper. You probably don't have room right here. So I would flip my notes over to the very back that's blank and do it on the back of your paper. Look at your ruler. What is your ruler measured in? Okay, one side's inches, one side's centimeters. Right? Make sure you're on the centimeter side. How do I know which one's the centimeter side? It's the smaller one. So, and how many millimeters are in a centimeter? 10. So each of those little bitty ones is 1/10 of a centimeter. So when you're trying to do 9.6, that means you're going to go to 9 and then count 6 little tick marks past, right? Same thing with 5. So you're going to create on your paper. I'm going to create it up here on the board, and we're going to compare our answers. So make your scale drawing. Label it when you're finished with your correct units. Does yours look the same as mine? This is what I love about this example. Does yours look like yours is bigger than mine? Yeah, but watch. It's really not. Is that not crazy? It's the same exact size. Can you guys tell when I hold them up to each other?
Yeah.
It's because my board is so big compared to your small paper that it looks different, the perspective. Any questions on how to create a scale drawing? Yes, sir. Possibly. If it says to create a scale drawing, you'll need one. That was on your supply list day one, though, back in August. So if you don't have one, you'll need to sign up for Encore or come in before school and use mine, okay? It won't be that you need it for a bunch of problems. So if you need it, it's probably just for one question. Okay, last thing in the notes. This is probably the hardest part and very important. So look at this and then we'll be done. We're going to do one more example. This is our relationship from what we've learned about similar triangles and then how it relates to perimeter and area. Okay? So if we have two triangles are similar, we know that that means that all of their corresponding angles are congruent and all of their corresponding sides are not congruent, proportional. That was day one. Remember, definition of similar triangles is all corresponding angles are congruent, all corresponding sides are proportional. We learned what was called a similarity statement, and we learned what was called the similarity ratio, which was the reduced value that we got when we compared 5 to 10, 3 to 6, or 4 to 8. Does everybody agree that those are all 1/2? Okay, I feel like some of you are not paying attention with me right now. Focus with me for just 2 more minutes. Are you with me that these all reduce to 1/2? Okay, and that's called the similarity ratio, right? And you did that on the homework that you just turned in. You found the similarity ratio and you found the similarity statement. Okay, so what's new in this section right here, Corbin, put your ruler down, is the perimeter ratio is also going to reduce to the exact same value as your similarity ratio. It's also going to be 1/2. Let's check it. To find the perimeter of this triangle, what do? Add all the sides. So what's the perimeter of this triangle? Everybody agree? 5 plus 4 plus 3 is 12. Okay, the perimeter of this triangle. 10 plus 8 plus 6 is 24. And what is 12 over 24? 1/2. Every single time, the ratio of two sides will be exactly the same as the ratio of the perimeter. Well, we're going to be able to use that to find the perimeter of a figure when we don't know all of its measurements. So this is going to be helpful. These will always be the same. The ratio of the sides will always be the same as the ratios of the perimeters. Okay? The area is a little different. Let's find the area of this triangle. How do I find the area of a triangle again? 1/2 base times height. What's the base of this triangle? 3. What's the height of the triangle? 4. What's 1/2 of 12? 6. Is everybody okay with the area here is 6? Okay, go to the second triangle. Area. 1/2 base times height. What's the base of this triangle? 6. What's the height? 8. What's 6 times 8? What's 6 times 8? Come on, guys, you should know your multiplication tables. 6 times 8 is 48. What's half of 48? 24. What is 6 over 24 reduced to? 1/4. That's not the same, right? But what is 1/2 squared? When you square 1/2, you don't need a calculator to do that, although you can check it on your calculator. You just simply square the top and the bottom. What's 1 squared? 1. What's 2 squared? 4. So the relationship, and this is super important, the relationship between the ratio of the areas If you take area over area, it's not the same, but it is the ratio of your sides or your perimeters squared. Okay, so in the next little slide, you'll see this all written down. If the similarity ratio is A to B, then the ratio of the perimeters is A to B. With me, Ribbon? But the ratio of the areas is going to be A squared to B squared. Okay, if the sides are A to B, the perimeters are A to B. But the area is A squared to B squared. So we think about square, you think about area being units squared, so it kind of goes in together. Let's look at our last kind of problem here, and there's a typo. This should be given that triangle LMN is similar to triangle QRT. And actually that should be QRS. So there's all kinds of typos there. Okay, they want us to find the perimeter and the area of triangle QRS. When you look at triangle QRS, do you have enough information to find the perimeter? No. Do you have enough information to find the area? No. But what we can use is this relationship that we just learned, that the ratio of the sides is the same as the ratio of the perimeters. So I'm going to write that down, write it with me. The ratio of the sides will equal the ratio of the perimeters. When we say ratio, what does ratio mean? Okay, and when we compare them, we write them as a fraction. So ratio is another word for fraction. So what are two sides in the picture that correspond? 13 and 9.1, or LM and QR. So we can say 13 over 9.1 should equal, and then we can compare the perimeters. So what's the perimeter of the first triangle? 36. So we can put that should be equal to 36 over, and we don't know what the perimeter is. That's what we're trying to find, is the perimeter of that triangle. So we can just put X or P. I'm going to put P for perimeter. Does this make sense? So side to side should be the same as perimeter to perimeter. Those are always going to be equal if the two shapes are similar. So we cross multiply, and we get 13P equals, I'm sorry, say it again. 327.6. Divide by 13. What is the perimeter? 25.2. Somebody agree? Okay, and what are our units? Centimeters. So we just found the perimeter without even knowing the dimensions of all the sides, because we knew that the two triangles were similar, which means they're growing at the same rate or decreasing at the same rate. So that means that the ratio of these two sides will be the same as the ratio of the two perimeters. Questions? Okay, now we have to do the area. So now we're going to find the area, and again, we don't have enough information to just calculate it, but we can use this concept. Oh, there's my color. We can use this concept that the ratios have a relationship. This time it's different. The ratio of the areas that's terrible, now it won't let me write. Let's try again. Areas, I don't know, I give up. The ratio of the areas does not equal the ratio of the sides. It equals the ratio of the sides what? Squared. So the ratio of the areas will equal the ratio of the sides squared. So you're going to have to square the sides and then set them equal to the ratio of the areas. That's a 2. Okay. So let's plug in our numbers. I'm going to do that over here on the board. So we're going to have the ratio of the areas. So what's the area of the first triangle? Area of the first triangle was 60. Over, we're looking for the area of the second triangle, so I'm just going to call that A. Is that okay? Equals, and then instead of just putting the ratio of the sides, we're going to square those when we write those down. So instead of it being 13 over 9.1, it's going to be what? 13 squared over 9.1 squared. So the ratio of the areas will equal the ratio of the sides squared. Okay, and now we're going to do that. So 60 over A equals, what's 13 squared? 169, right? And what's 9.1 squared? 82.81. And then we're going to cross multiply. So we have 169A equals, what is 60 times 82.1? 1,900, oh, sorry, 4,000, go ahead, 0.8, and then we're going to take that and divide by 169. 0.6 instead of 0.8, so double check. So it is 0.6, okay. So now divide by 169, and tell me what you get for the area. 29.4. And what are the units? Very good. Be careful. Area is always units squared, so it should be centimeters squared. Any questions? Okay, guys, so